Hello, my name is Denis Efremov and welcome to my presentation. This is a tool presentation. The tool is named CVEHound. What it is for? It automates the checking of kernel sources for missing fixes of known CVEs. I started this project about 10 months ago. The tool works as a static analyzer, and to detect missing CVE fixes, the tool doesn't use kernel version, doesn't require a development log, and doesn't need to know how to build your kernel. But internally, the tool contains a special rule for each CVE it is able to check for. As for now, I describe it more than 200 kernel CVEs. The main value of the tool in these descriptions, and I will talk about them in detail a bit later. Additionally, the tool supports various filters like search in subdirectories or specific files. Checking of code only enabled in a build config also supported. Kernel config analysis is based on the Undertaker project's code. I reuse CVE metadata from linuxkernelcves.com for information like CVE and CVSS scores. This is a very hard work to collect and maintain the metadata and many thanks to the project. Not so long ago, I also added reports generation in JSON for CI systems. Let's talk a bit about why, in my opinion, do we need to automate these checks and why the automation is not so simple. I'm pretty sure that you all already know these facts, but I would like to explicitly mention them once again in my motivation part to give you a better understanding of why the tool works this way and not another one. Some automation is highly desirable because we've got thousands of CVEs assigned to the Linux kernel. Most of them are in recent years. Records are in different databases and many databases are somehow synchronized with each other. Lack of information about vulnerable versions, wrong commit references, it's a common problem for many records, and moreover, we've got national databases with alternative identifiers. For example, in Russia, there is a stack database with BDU identifiers. And you can't just take a kernel version and check whenever your kernel is vulnerable or not, because you need to know vulnerable version intervals for many kernels like stable, LTS, XLTS, super long-term support, and even after that, you will face that there are kernels with, I would say, an independent backporting process. And sometimes when you do your own backporting, you take also features from mainline to, for example, speed up the things, or you backport even full drivers. And in this case, the information that a specific vulnerability was in a mainline kernel version from version A to version B gives you very little information. Moreover, the kernel is a highly configurable project, and some configurations are vulnerable while others aren't because a driver is simply not enabled. It's a common workflow when developers backport only fixes for kernel paths they care about. After all, why would you care about a floppy driver if you prepare an Android kernel? Git log is not always available to you because, as far as I understand, GPL license doesn't require you to publish a development history. And even if you have an access to it, without being a kernel developer, it's very hard to say what CVEs are fixed and what are not based on the log. Because there can be revert commits, an early version of patches for mailing list, and many other things. When I started tool development, I kept in mind a couple of use cases. For example, let's imagine that you are an engineer in a certification lab and you have full sources for a device, and one of the requirements in a certification procedure is that all known CVEs should be fixed or mitigated somehow. So you need to check maybe 100 of CVEs in the kernel. Or maybe you are a system administrator and you can just update a kernel because of third-party modules that simply don't work with newer kernel versions. And you want to know what administrative measures you need to take to mitigate possible bad consequences of an attack. So you need to start by getting a list of CVEs you need to take care of. Maybe you are a pen tester and you don't want to find new exploits. So just extract the config file from working kernel, take the closest possible kernel version, and get a list of CVEs to check on a device. Or maybe you are a kernel developer and you are doing your independent backporting, and you just want to double check yourself. Maybe you want to enable additional kernel modules like one of network file systems on your phone, and you also want to check the state of these drivers in a tree before enabling them and making your phone vulnerable. As I already said, developers sometimes don't backport fixes to not enable drivers. So, how to implement this kind of checker? Actually, we've got one in the kernel for more than 10 years already. It's called coccinelle. Without reinventing the wheel, I use it in the CVEHound tool. Many kernel developers already use coccinelle and know how to write rules for it. Coccinelle is a static analyzer that allows you to describe C language patterns in a C language with additional meta expressions and find real code that falls into these patterns. Here's an example of coccinelle rule. It describes a code pattern when we copy data from user space and compare it to some node string in the kernel. The pattern is a code with copy from user and string compare calls with upper E meta variable to match variables and pointers and ... notation to match everything else. The coccinelle will find many different functions for us that fall into this pattern in the kernel. Usually, it's that's what you want when you write a rule for a static analyzer. And to make this rule as many cases as possible, cases of API misuses, for example. But in the CVEHound tool, I want a contrary thing. I want to search only for one case in the kernel and check it, is it present in the kernel or not. So I add additional details to the rule to make it more strict, to detect only one case, but detect it through all changes from the commit where it was introduced to commit where it was removed. Breaks commit where vulnerability was introduced and to the fix commit where it was removed. So I still need to abstract out from such details as, for example, variable names. Some statistics to give you a better feeling of how much effort you need to take to write these detection rules. I started the project about 10 months ago, and since then I have described more than 200 CVEs. Most of them were assigned to the kernel in the last 3 years. I spent only 42 days adding at least one detection rule to the project, and there were only 8 days when I spent the whole day writing rules. Usually I can describe more than 10 rules in a single day. Each rule is tested that it detects a CVE in the interval from breaks commit to the fix commit, and each rule is tested outside this interval that it doesn't detect a CVE. To write a detection rule, I take a commit that introduces a bug and a commit that fixes it. I need these commits only to test the rule, otherwise I don't need them. Like I already said, the tool doesn't need a git log to work. Sometimes finding a fixes commit is not trivial. I even maintain my own list of wrong fixes tags that I found in different fix commit. Usually it takes about 5 to 10 minutes to draft an initial version of a rule and about 10-12 minutes to test it. There can be many iterations of refinements and testing. Let's have a quick demonstration. I reverted a floppy fix from 2018 on top of 5.13 kernel. And usually, to run the tool, all what you need is to specify a path to the kernel sources directory, but I'll also limit the search to floppy.c. And the tool will find it for us. Just to give you a bit more information, the tool internally calls coccinelle with different patterns, and coccinelle also outputs a line number of a match for us. To check a kernel config option, you also need to specify a path to .config file. And in this case, the tool will output for us a config option that enables floppy.c, and it will also check .config file for this option, and it's indeed enabled. Another example. Here, I partially reverted two capability checks on top of 5.13 kernel. The original patch adds 4 of them in different functions, and I reverted only 2 of them. And the tool will output for us exactly 2 lines of the functions where capability checks were removed. And I would say it's pretty common when there is an error in backporting, or you accidentally revert parts of the commit later. Let's get back to the slides. Let's look at rules and some typical patterns that are used to describe a CVE. We will start from simple cases and move to more complex ones to give you a better feeling of extensibility of this approach. CVE on the left just removes some code from the kernel, and in this case we can simply search for removed code, and if we will find it, it definitely means that the fix wasn't applied. CVE fix on the right adds a capable check, and to describe it we use some real answers like function name, global variable name, and abstract out from details like local identifier name, and use ... to match everything else. There is a ... when not equal notation that means match everything if it doesn't contain this line. So we'll match row sock create if it doesn't contain capable call before assigning row sock row oops to a pointer. And later I also added ns capable call because capable was changed to it. Here I use another approach, and instead of using ... when not equal, I prepared 3 patterns and made them depend on each other. So in the patch, we just add an initialization we just add another entry to a global array, and to detect this, I need to check that there is indeed such constant in the enum definition. It was introduced in a separate page. I need to check that there is a global variable, and I need to check that there is no initialization for this global array with this constant. So instead of writing ... when not equal, we can write a pattern and check that coccinelle can find it in the sources. Let's move to functions that change existing lines of code. The error here is self-descriptive, wrong permissions, and in the patch we simply check for them. In the rule, we simply check for them. This is a simple case when a fix fully describes an error and diff contains full information that we need to write detection. With this slide, I want to show you that in most of the cases, diff doesn't contain enough information to describe a CVE rule. So in general case, fix doesn't contain full information, and like for this function, raise access for a global variable, the patch just adds mutex lock and mutex unlock to one of the functions, but the error is in the combination between these 2 functions, and to properly to reliably detect missing fix, I need to describe both of the functions, but because one of the commits adds 1 function with mutex logs inside it. Another commit adds another functions, and third commit adds a global variable, and the error is in combination between them. Here is another case, a simple patch that initializes a local variable, but to describe it, first I need to check that there is a structure with a reserved field inside it. I don't remember exact details, but highly likely there is no information leak if there is no reserved field in the data structure definition. So we check here for the field, for the copy to user call, and we check for absence of initialization. And these receptions are enough to describe most of CVEs on practice, but sometimes coccinelle is not enough because it's only suitable for matching C code patterns. And like in these cases, with errors in an LD script and assembly changes, you need to do different things. In a coccinelle rule, you can write a Python code, and in this case, with an LD script, I check that in Python, I check that an LD script contains a special string with a regular expression, and I depend a pattern match on this check before reporting an error. And in our approach is to fall back to regular expressions. And in this case, for CVE, it's also possible to write a coccinelle rule, but I decided to try a grep mode with a PCRE. Regular expressions are not very readable, but they are very powerful with all these look ahead and look behind expressions and many more features. So that's pretty much all approaches that I use to describe CVE patterns. Future plans. Short-term plans include adding the tool to the kernel side testing workflow. I already started to do this. It should be the same as adding a coccinelle. I see no value in checking stable trees because I already do this when I develop detection rules. But it can be interesting to check trees that are based on stable branches. And I also want to add more precise analysis for kernel config options. As for now, it's done on a per file basis, and if there is an ifdef inside a .c file, the tool may report incorrect results. And I also want to add a filter for checking files enabled by a specific config options. Like I already said, let's suppose you want to enable a couple of config options on your Android kernel, and you want to check is it safe to enable them or not, and you don't know what files will be built if you enable them. A midterm plan is to add another checking mode to the tool. This lightweight mode will check only the git log, and some of my colleagues asked me to implement this, and this mode will be useful mainly for kernel developers. The simple idea is to check that there is a breaks commit in your branch and there is no corresponding fix commit in the Git branch. I already drafted an initial implementation for this, and of course you can just check for commit IDs because they are different in different trees, so you need to take into account things like commit title, commit author, commit time to really check a Git log. And there are many hidden stones here with revert commits, multiple commits that fix one CVE, and of course you need a very good mapping between a CVE and the breaks commit and fixes commit. And long-term plan is to automatically generate detection rules based on a breaks commit, fixes commit, and history between them, and maybe some manual markup like this line should be present in the sources, and this line should also be present in the sources, and this line should not be present in the sources, and I'm pretty sure it's possible to generate detection rules in more than 80% of the cases. This is the end of my presentation. Thank you for your time. Any questions?